Oh, I haven't.
Can you guys see that okay?
Yeah.
Okay. And sorry about my voice. This is about all I got. It's bad. I'm okay. We'll start in like 2 minutes. Alrighty, guys. So again, those of you who just got in, that's about all I got for my voice today. Which kind of sucks. But I'm just here to help you guys get ready for the quiz and then also do the pre-lab question help as well. So we're going to start with question 1. I have different apps. Can you still see the screen with the drawing?
Yeah.
Okay, good. So let me do this. I have like an organic chem app and then I have like this open. So when we're drawing D-glucose and it's a Fischer production, you know it's going to look something like this. Remember, when you say Fischer, let me just make sure I have it right. It's going to be this line type of structure. When we're talking about the cyclic structure, then it's going to be a ring when it comes to carbohydrates. So glucose, and really the only way that you guys, there's really no way to help memorize, just kind of get these down because you will have to memorize these for tests. And so at this end of the glucose, there is an aldehyde group. And remember, each of these intersections represent a carbon. And so off of the first carbon, there is, let me just make sure I'm doing this right. There's an OH on this side and then an H on this side. So sorry, my H's are kind of bad. Try text. Then on this side, oh, that's humongous. Okay. I'm not gonna do that. I'm gonna do this. H, OH, and then these last two, and we're looking at D-glucose. So D means that on this bottom carbon, the OH is going to be on the right side. So it was L-glucose, which L I just think of as the left. The OH would be on the side where the H is now. So remember, since this is a D, the OH is on the right side. Okay, I'm not even going to attempt to write that out, but just make note of that. And so then at the bottom, there's a CH2, and I'm sorry that my drawing is awful, OH. And that's going to be at the bottom. And that's going to be pretty consistent with every carbohydrate you get. There's going to be that aldehyde at the top, and there's going to be that CH2OH at the bottom. Again, sometimes it does vary, but our basic ones that we're going to be looking at, like especially on the quiz, that aldehyde at the top, and then that CH2OH group at the bottom. That's how you would draw D-glucose. And again, I just like to memorize when I'm going with these, the molecule name, how many of the intersections it has, and then I memorize where the OHs are. So this one would be OH, 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 and then for one T, OH, and just memorize it like that, break it up into those 3 sections. Because some carbohydrates, they don't have 4 intersections. So just remember that that specific one has 3 or has 4. And that's how I would go apart memorizing it. So this next part, if we're going to be looking at this carbohydrate, and show them how to categorize this as a hexose and an aldose. So let me look at my notes super quick. So when it's an aldose, I just mentioned this, it's going to have that aldehyde on the top end. And so again, remember aldose, aldehyde, always going to be top end. If it was a ketose, then it would be a ketone at the end. So that double bonded O at the top, instead of a hydrogen being next to it, it could be another carbon or a string of carbons. Hello?
Oh, I'm so sorry. I did not know I was on mute. Or
You're
not.
okay. You're okay. You're fine. Sorry. So again, aldose, aldehyde, ketose, ketone. A hexose means that it's going to be, actually no, I lied. So hexose means 6 carbons, because hex 6. So there's 1, 2. So there's 1 at the top. There's 4 intersections. So that's 4 in the middle, and then another one on the bottom. So that makes it 6. If it was a triose, there'd only be 3 carbons, meaning that there'd probably be one at the top, 1 of the intersections, and then 1 at the bottom. Say it was, let's just say a pentose. There'd only be 3 intersections because there's 1 carbon at the top, there's the 3 in the middle, 3 intersections, and then 1 on the bottom, making that 5. Does that make sense to everybody how you would classify those? Good. Again, you can tell this is a D sugar because the OH on that bottom, right before the CH2OH, is on the right side. If it is an O sugar, it would be on the left side. I feel like that one's probably the easiest to memorize because O means left. And D, it's like some weird like dextro-rotary type of word. I don't know if she used that term, but if you see dextro something, then know that that means D and that means right. Is everybody okay with carbohydrates? I would suspect on the quiz, maybe a drawing of glucose, but possibly an L-glucose. So again, the exact one that I drew before. But this OH on the bottom be on this side if it was an L. So those 2 would be switched. I would also, more likely you're going to get a question like number 2, where you get a carbohydrate and you have to kind of classify it. So if there were 7 carbons here, heptose, and stuff like that. Is everybody good with this basic structure of carbohydrates? Okay. Next up, we're going to complete the reaction below. So let me draw this out super quick. Okay. This is going to be really fun. Here we go. And that's very effective. And then we can do well, that was awful. So I'm just going to draw on this and hope for the best. All right. So this is the molecule that we're starting with. And when you add acid and then a specific alcohol. So this one that we have in this example is just methanol. It's OH. And then there is, I'm going to use the shorthand for methyl here since it's just a CH3. So don't get confused. It could also, if it was a CH2, CH3, you could write the OH and then et for ethyl. So that shorthand will just make it easier when it comes to drawing. So remember, when things are hemiacetals, this is when you're trying to protect that ketone or aldehyde and make it into something else so that it doesn't react. So when you're going to be doing this, you're going to be converting whatever ketone or aldehyde into a substituent that involves this new alcohol that's being introduced. So the hemiacetal is going to be one of these alcohols groups. So OMe. The OMe is going to bind once, making it the hemi, because it's not bonded twice. And then, since the carbon needs another bond, it's not just 3 bonded carbon, there's that OH there. So when she asks for a hemiacetal, you're always going to have one OH because it's not completely converted over to the alcohol yet. Then you're going to have one version of the alcohol. And again, for that oxygen to bind to that carbon, you're going to drop that hydrogen. And so a common mistake on a test, which I have definitely like 100% done, is accidentally written this. You do not want to do because that's not accurate, that hydrogen does leave. But if you do, you're not going to get like major points deducted. It just means you forgot to remove the hydrogen. And then we have this molecule right here, the OMe, and then the OH. I don't know why that is so big. And you're going to run it through that alcohol and the acid again. This time you're going to get a full acetal. I'm just going to write it in cursive because that'll be a little easier for me. So when it's no longer a hemiacetal, you're no longer going to have that OH group, and it's going to be replaced by another alcohol group. That OMe. Now, just for some food for thought, in both of these molecules, you are creating an ether. So we've learned about those. And you know it's an ether because there's that oxygen in between 2 different carbons. So there's a methyl here. And then don't worry. Wait a second. You will never be expected to name this. At least not on any quiz or exam in the upcoming future. You do not have to name these. But it is cool to know that they are ethers and they are made. Does that make sense? The hemi versus the acetals? Sorry, I'm coughing a lot. Do not get your tonsils out. That is a pro tip from me. It's not a fun surgery to recover from. All right, so this one's kind of split up into 2 pages. So the molecule below, for hydroxybutanol, easily forms, and a correction here is a 5-membered ring. So just know that in this 5-membered ring. Sketch the hemiacetal. So we're gonna click new, and we have our molecule here. I believe it is an aldehyde. Yep, because there's that H at the end. And then there's an OH. So when you are forming that hemiacetal, this time we're just going to be adding acid. Doesn't need a specific acid or specific alcohol because we're going to make this into a ring. And so the way you'll know to not make it an acetal like the one that we just did is if there's no alcohol underneath. So if it's just the acid, you know that it's probably just going to be a ring. So we're going to sketch the hemiacetal and we're going to go through the numbering system. So we start numbering. Give me a second. Yep. We start numbering at this carbon with the double bonded O. So 1, 2, 3, 4, and then it's attached to this oxygen down here, which makes it 5. And so I'm going to make it like this. So that is a 5-membered ring. And so if I were to number it, 1, 2, 3, 4, 5, and then off of 1, there is that OH. Now remember, it is a hemiacetal, and so you are going to have this OH hanging off because once it becomes a full acetal, there's going to be no more OHs. So if you write this, if you write the OH up here, that is correct, because remember, hemiacetal. And the reason why it's not, I guess, like no acetal is because that other alcohol group or that other substituent is being bonded to this oxygen. So this is the 5-membered, it's a correction, 5-membered ring for this molecule right here becoming the hemiacetal. And again, I numbered starting at this carbon is 1, and then the oxygen that closes my cyclic, that is number 5. Does anyone have any questions about that? Because I know that's a little difficult.
I have a question. So the OH, is that gonna turn into the O because it's at the 5, and then the double bond O turns into the alcohol?
Yep, that's exactly it. Yep. Again, when you're doing this, usually, right, this aldehyde is going to be what's making the OH, which is shown, that's that OH. And then the other bond off of that could be whatever the alcohol is, or in this case, it turns into the rest of the ring. So that's exactly right. The aldehyde becomes the OH, and that alcohol becomes the O that is in the ring. So the reason why 3-hydroxypropanol doesn't work as good, or doesn't easily catalyze, let's do this. Yeah, so 3-hydroxy, yeah. So the reason why this doesn't work as good is because when you start numbering, right, 1, 2, 3, 4, it's only going to make a 4-membered ring. And if we remember, 6 and 7-membered rings are the most stable, along with 5. So 5, 6, 7. 6 is the most stable ever, and so the ones around it, 5 and 7, are also pretty darn stable. Once you start getting smaller, right, this is what the ring would look like. Okay, that's really bad, but here you go. That's even worse. So I'm going to attempt to draw this a little better. Okay, much better. So this is what the ring would look like. This is not very stable at all. And so this is not easily going to become a ring, like it would be with the 5-membered ring. If it was a 6, say this had 6 carbons on the chain, it'd be super, super ready to turn into a cyclic. Say there was only 2 carbons, right? This would make a 3-membered ring, which is even less stable. And so when asking about stability, 5, 6, and 7 are the most stable types of rings, which is why they form those hemiacetals so easily, because they want to go to the most stable form. But when you have a molecule like this, or like this, with 3 or 4 carbons, that would be in the cyclic. So this cyclic would look like, I guess this would look like a triangle. That's not stable at all, and so it's not going to favor that. Does that make sense? Everybody good with that? Again, if you're going to get a question on that, just all you really have to say is that 5, 6, and 7 numbered rings are the most stable, and then rings with less carbons are less stable. That's all you have to say. Next up, we have storing all of the chiral carbons in the molecules below. So I'm going to try and draw directly on the page because I don't want to try and draw these out. So if you guys remember, when a molecule is chiral, that means it has 4 different things around a single carbon. So when a carbon is chiral, it's 4 different things around that respective carbon. So if a carbon has 2 methyls around it, it's not going to be chiral. It needs to have 4 different substituents. So I'm just going to go through each of these carbons and basically explain why they are or are not chiral. So this one right here, the one at the end, can you guys see my little mouse moving? Just give me like a thumbs up if you can see my mouse moving.
Yes.
Okay, sounds good. Thank you. So this carbon right here is bonded to 1 carbon here and then 3 hydrogens. So since it's bonded to 3 of the same thing, it's not going to be chiral. And it's the same for this one here. Bonded to 1 carbon, has 3 hydrogens, not chiral. This carbon here is bonded to this whole big chunk over here, but it's bonded to 2 methyl groups, 2 carbons with 3 hydrogens. So this carbon right here is not chiral. This carbon right here, it has this big group here and this big group here. And even though those are different, it's still bonded to 2 hydrogens. So that one is not going to be chiral. Let me just write in some of these hydrogens. Hydrogen here, and a hydrogen here, and a hydrogen here. All right. So this one is looking like a contender because you only have it bonded to 1 hydrogen, so that's 1 different substituent. There's the methyl here, so that's 2. There's a big group over here, that's 3. And there's this big group over here, which is totally different, so that's 4. And so this carbon right here, I'm just gonna kind of heavily circle it. That one is chiral because it has 4 different things coming off of it. We're gonna keep moving. This carbon up here has 3 hydrogens attached to it and the carbon, so 3 hydrogens means it can't be chiral. This one right here has 2 hydrogens coming off of it, so it's not chiral. This carbon right here has bromine, so that's a different group. Has a methyl, so that's different, so that's 2 different things. Has this big group all over here, so that's a 3rd different group. And then it has this purple group off to its side, so that's 4 different things. This carbon right here is chiral. So if you keep going down the line, these 2 carbons here, they both have just 2 hydrogens attached. So I'll draw it in for one of them, not the other. And then this carbon right here, again, this is just attached to 3 hydrogens and it's in the 1 carbon there. And so that's not chiral. So for this molecule right here, there are 2. I'm just going to write CC for chiral carbons. Next up, we have this molecule right here. So if we're gonna, I always start left to right. I don't go right to left when I do chirality because it just makes me confused. So I always start on this side. This side, this carbon has 3 hydrogens attached to it and one carbon. So 3 hydrogens, 1 carbon, 3 of the same thing, cannot be chiral. This one has a hydrogen attached to it, an alcohol attached to it, so that's different. It has a methyl group to the side, then it has this big structure over here. And so since all 4 substituents bonded to the carbon are different, that is a chiral carbon. Now we're going to move down here. This one's kind of tricky, and you will see why in a second. So this carbon has 1 hydrogen coming off of it, and then it has an alcohol coming off of it. So that's 2 different things. Then if you look here, these 2 substituent groups are exactly the same. They both have this ethyl here, and then there is an alcohol group right there. And so since there is symmetry in this molecule, this middle carbon, which is the center of all the chemistry, you can split the molecule right down the middle. Since 2 of the substituents are the same, this and this are the same, this middle carbon is not chiral. Does that make sense? Any questions about that? So there's any sort of symmetry in the molecule, wherever that symmetry is coming from. So right here, can you split down the middle? That middle is not going to be chiral. We move over 1 more carbon, right? This one has a hydrogen, an alcohol, a methyl, and this big group over here. And so this one would be chiral. So these 2 can be chiral, even though it's in a symmetrical molecule, because they don't have the same substituents coming off of each one. Like, that was kind of weird how I worded it. They don't have multiple of the same substituents coming off of themselves. So this one, not chiral, these 2 chiral, and then this one is the same as this one with the 3 H3s, or sorry, 3 hydrogens, and so it's not going to be chiral. So this one right here also has 2 chiral carbons. Does that make sense about chirality? Do I need to do more examples of, oh, I'm sorry, I didn't see I had a chat. Oh, yeah. Yeah, so any questions about chirality? Any questions from here that you'd like me to do another example of? If so, you can put it in the chat. That's the entire worksheet. So it's not a lot that you have for this quiz. It's a bunch of random things. So like there's carbohydrates, then chirality, and then hemiacetals. An example of number 2 again. This number 2. This number 2. Yeah. Okay. So I'm just going to draw a random carbohydrate and we're going to classify it. So I'm just going to, here we go. Okay, that OH is really sad, but it's okay. So I'm going to draw something unlike anything that we've seen yet. So I apologize again for my shakiness, but I will explain what the drawing is, obviously, as we go on. So the first part of this problem asks us to classify whether it's an aldose or ketose. So here we go. Here's the top. Here's our carbonyl group, our double bonded O. And instead of a hydrogen on this side, okay. And so instead of a hydrogen on this side, there's a bunch of carbons, making it a ketone. And so this specific, let's see how this works. Okay. This specific carbohydrate is going to be a ketose because there is that ketone branching off of it. Now it asks us to count whether it's a pentose, hexose, heptose, anything like that, triose. So I'm just going to count all the carbons now. So I'm going to start up here. 1, 2, 3, So I'm gonna make this a little bit shorter off of this end. I'm just gonna chop this. So imagine this is just a carbon here. So I'm actually gonna start. So 1, 2, 3, 4, 5, 6. I just wanted to get rid of that so we wouldn't have to do like a crazy pronoun or anything for any crazy preposition. So there are 6 carbons in the sugar, which would make it a hexose. So this is a ketose because of the ketone at the top, and a hexose because there are 6 carbons total in the molecule. Another question asks us, is it a D or an L enantiomer? So I'm going to look at this bottom carbon right here, this last little branch off. The OH is on the left side. And so since it's on the left side, it's going to be an L enantiomer. Then if it was on the right side, it would be D. And so that's how you would do a molecule like that. Again, remember, count your carbons. So you get whether it's a pentose, hexose, heptose, whatever that, again, whatever prefix that is. And then ketose versus aldose, whether it's a ketone up here or an aldehyde. So we have a request to do the second carbo molecule again. Let me look super quick. Favorite question. Second carbo and the second molecule again. Yeah. So this is the second carbon in the molecule. And it is chiral because it has an OH coming off of it. An OH coming off of it. An H, a methyl, and then this big group over here. And so since it has 4 different substituents, it is a chiral molecule. Now, if we were looking at, again, this middle carbon, there's an OH coming off of it, there's an H, so that's 2 different substituents. But then these 2 halves of the molecule, if I split it right here, this is the same, and this is the same. And so there is not 4 different substituents coming off of this carbon because these 2 halves are the same.
I guess she's a super spreader too. Not Alexa. Oh yeah, I was like Alexa. I don't care.
Does that make sense? This one is symmetrical, and then these 2 are chiral. Pretty good. Any other questions about this worksheet specifically? Again, I don't know how much she told you to memorize because I wasn't in class the Friday that we had it. But I would memorize glucose because that's a very important one. Just remember, D is right, L is left. Again, the hemi and acetyl questions are probably going to be some of the easiest, at least the ones with the alcohols on them, because all you're doing is, again, OH, and then whatever alcohol is in the problem. This one's a ring. Always start numbering at this one, and you end at this one. This is 1, 5. And then chirality, just be really careful. I would mark where all the hydrogens are on every single carbon molecule, just so you know whether a molecule is chiral or not, if it has 4 different things attached to it or not. That's just a way to get your thoughts together and to visualize it well. Okay. That's all I have for the worksheet. So if you guys have any questions at the pre-lab, I still have about 20 minutes. So we did the acetyl problem. Yes. So we can do another acetyl problem. We'll do another acetyl one just because those are going to be some of the easier ones that you're going to be getting. And I'm just going to make one up myself. So I'm going to do, that's really bad, but it's okay. I'm going to do something you're probably going to see on the test. And again, this right here, this ET is an ethyl group. So this, you could write that out. Let me see if I can. So that's just another way to write it out. If you wanted to, the CH2CH3. So when something is a hemiacetal, hemi means that it's not going to be substituted completely. There's still going to be one OH coming off of it. And then OET. When it is hemi, the alcohol will be substituted once and making it ether. And then the OH will be on there once. Then when it is an acetal, you're going to be taking this molecule and keep it going with the acid. And you're going to get, let's see if I can type this, make it a little bit neater. You're going to get the OET and OET again. Does that make sense? So again, when you're doing acetals, especially ones where you're given an alcohol, those should be the easier ones that you're getting. Remember to always drop this hydrogen here. I crossed out the, there we go. Always drop the hydrogen here. Common and easy mistake. All right, so I'm getting a bunch of questions about number 6 on the pre-lab. So let us switch some gears. If you guys are good with the pre-lab, feel free to head out. Don't mind. We're just gonna look up the pre-lab super quick. And pull it up. And again, remember, you can drop that off to Nagala, either at his office, or I think it said in room like 201 in code. I'm not exactly sure which room, but I know that he posted that on Canvas. So let's look at this pre-lab. All right, so number 6. This one is a tricky one, especially since you guys haven't gone over it in class. So we're going to draw the structure of caffeine. So I'm just going to look up the structure of caffeine. Give me, here we go. Okay, so this is caffeine. Now it says to identify functional groups on the caffeine molecule. So functional groups are anything from ketones, aldehydes, alcohols, anything like that. Again, here's the full molecule. All of those are functional groups. So when you're looking at this, you know that there's going to be methyl groups coming off of it. So you could write methyl. These CH3s are methyl groups. Oh no, what have I done? Two functional groups present on the text. Yeah, so when you're looking up functional groups, literally, you can even look up, you can do that right. Functional groups of caffeine. So there's amines here and amides, and you haven't quite learned about those yet, but it did say that you could use your resources to help find them. So again, here's 2 that are set in stone. You can use these in your example, perfectly acceptable. There's an amine and an amide. So when it comes to IR, you're going to get basically this weird looking graph. I'm going to look it up for you just to kind of show what it would look like. You're going to get a graph that looks something like this. And again, this is hard because you guys haven't learned about this yet, but each of these different functional groups, like there's an amine and there's an amide, there are different absorbance levels, which means there's going to be different peaks at wherever there's an amine or an amide. So if if a molecule doesn't have an amine or an amide, it's not going to have peaks where those functional group absorbance are listed. So we're just going to do it based off of these two examples, amine and amide. And again, this one you would have to look up like basically completely. There's no way that you guys would know how to do this one without looking it up. So just cite where you're finding the information. So what signals will I look up? I'm just going to look up IR signal or amide. And it gives you something here. Or amide. And don't get, some of these are a little crazy, but you can even just look up a basic website and it should give you a reading. And how you would write it is basically that range. It's going to be a number range, usually in the thousands. So for this example, I don't know, my computer's kind of swollen. I'm looking right here. Let's do an amine because I see that right now. Here we go. An amine is going to be this right here, the 3500 to 3300. And then the label for that is going to be the centimeters to the -1st power. And look, this group right here, I would recommend taking a picture of this. If you're on your phone, screenshot this. This is actually a fantastic table because it also has the amide on it. And so this is going to be the reading if there's an amide. And so I'm guessing you guys are going to have to do IR for this one. What you're going to do is, again, you're going to get IR spectra for caffeine. You're going to get a chart that looks like this. It does not look like caffeine. So you're going to get something that looks like this. And you see these two peaks right here? Those are probably the amide and amine peaks. And so for that question, all you have to do is write down two functional groups and then look up their IR signals and then just cite where you found that information. So again, that one's tricky because you guys haven't learned it, but that one you're expected to look it up and get those signals because you don't have to know them off the top of your head. So I saw another question for the pre-lab. And we're going to look at question 2B. So, all right. So I was actually helping somebody with this one last night. And so percent recovery and mass percentage of the T. Percent recovery. Hey, Kira, can you explain what you mean for number 6?
You have a tab open for like what the structure is supposed to look like the chemical structure for caffeine. I just wanted to see what, okay.
Yep, take a picture of it. That's what it looks like.
Thank you.
Yep, you're all good.
Appreciate it.
You're good. All right, so number 2B. So percent recovery. You have this weight right here, right? You have this weight and you recovered this much weight from the experiment. And so sorry about that. So let me do this really quick. Mass percentage of T. So for mass percentage, you're going to divide what you got of caffeine by the total amount of T, because that's how much caffeine there is per the total mass. And so again, whenever you get mass percentage, you want to look at the whole mass and then the part that you get yourself. Percent recovery is, looking at question number 1, I believe it was, I don't know exactly how much, but it may be 55 milligrams. Let's just guesstimate around that. 55 milligrams of caffeine in 1 bag of tea. You know that there's 4 bags of tea that you're using in this reaction. So the expected amount of caffeine that you're supposed to have is going to be that 55 milligrams times 4. Which I don't know, again, I don't know the exact calculation. But that is going to be your expected recovered amount of tea. What you got was this many grams of caffeine that were recovered. And so, again, the difference between percent yield and percent recovery is percent yields when you're doing an experiment and you don't start with whatever like molecule you have, like you are trying to get to. So like last time we were making aspirin, we didn't start with aspirin. This time we're starting with caffeine. All we're doing is extracting that caffeine from the tea leaves. And so for percent recovery, you're going to be focusing on how much caffeine you were able to successfully extract based on how much there was. So the calculation for this one would be, you want to get that 55 milligrams times 4. And then you'll do then what you got, what you actually got, divided that expected, which is the 55 times 4 bags. And remember, this is milligrams, so you need to convert to grams because you got grams of caffeine here. And then percent recovery, you multiply that percentage that you get, this divided by whatever mass is expected, then times 100. And that's how you would do the percent recovery aspect of question B. Does that make sense? Everybody good with that?
Can you repeat that last part, please?
So again, when you're doing percent recovery, you want to do what you actually recovered divided by what you started with, that amount of caffeine you started with. So it'd be 4 times the 55 milligrams, which I believe is just 0.055 grams. So 4 times 0.055 grams in the denominator, then in the numerator, you have what you actually got, and times 100 because it's percentage. That makes sense? And I can go over mass percentage again too. Mass percentage is how much caffeine there is for the entire mass. So you do caffeine divided by the whole mass.
Is that multiplied by 100 too?
Mass percentage, oh wait, yes, mass percentage should be multiplied by 100 as well.
Okay.
Yep, so thanks for clarifying. Any other questions about the
I have a question, but like it's really not. I don't think it's regarding the pre-lab. So, can you like email? Do you mind emailing the?
Yeah, if everybody can just leave their email in the chat that would like the practice sheet that I gave out. Just send it in the chat and then I can email it to you guys so you have extra practice and you can go back over the questions that we did. Thank you guys. Now we'll get that out to y'all because I know that is important for you guys to have as a study tool. And yeah, so there should be any reason why you wouldn't be able to get that. So any other questions about the pre-lab? This one introduced a lot of different things that we hadn't really worked on before. So again, if you're okay to use the internet, just cite where you got it from and you're perfectly okay. If you don't have any questions, then you're free to go because we're at our time basically. So I will see you guys hopefully on Wednesday, fingers crossed. As you can tell, I'm not doing fantastically, so I'm doing my best to get better. And I'll be there for you guys, please. If that's all, then you guys can head out.
Thank you.
Have a good day, you guys.